Okay, so next up what we're going to do is create the function to solve the board. So we're going to delete these print statements. Don't need these anymore. There's one there and there is one right there. So our function is going to be called solve board. So solved board is what's going to be an output. So solved board, like this. That's equal to the output of solved board. Solved board is going to take in the board of colours, and I might pass in colours. No, actually, I'm not going to do this. So we'll just pass in the board, and that's all for that. Now, define solve board. It's going to take in an unsolved board, and it's going to return obviously a solved board, but we'll get to that. So this is the function I talked about in the last video that's going to basically call all of the different attempts at solving the board. So what it's going to do is it's going to possibly copy the board. I'm thinking what we want is we want to know when an algorithm's worked. So if we save a copy of the board at the beginning and then we go through an algorithm and then check if it's the same, and then what we can do is if it's the same, it moves on to the next algorithm, and if the board's changed, then it can repeat that one until there's no change. So for example, like if we go to this 9x9, because I don't think this can be solved by forcing, so what we'd do is we'd copy the board state here, we'd then attempt to see if there was a force move, and we'd do it, so we'd get this one here. We'd then finish the force move algorithm because we'd just done our force move, and then we'd come back into the solve board function, and then we'd say, is the new board equal to what the board looked like before it went in the function? And obviously in this case it's not, it's actually changed. So now because it's changed, we're just going to repeat. We're going to repeat the force move. So you can see there's plenty more force moves to make. So the idea is eventually we'll have done all these force moves. Something like this. Is that all of them? Yeah, so oops. So yeah, this one goes up here, that one goes up there, and then it's done. But obviously I can't do the two yellows at the same time. So then it's going to say, right, well, now we've done all our force moves and we're getting back to the same board when we run that function. So now we're going to try our second algorithm, which is going to be something probably not as robust as this. So we know that every move we've just made on this board is definitely right. All of these moves are right because there was no other option. The idea is our other algorithms that we run might not always be right, they might sometimes be wrong, so I would rather run the ones that are definitely going to give us right answers first, and try and like narrow down the solution space so that we get to a solution faster basically. So yeah, hopefully that makes sense. If not, hopefully it all makes sense once we get there. So first things first, we're going to have the original unsolved board. That's going to be equal to the unsolved board. Now we're going to run, we're going to call the unsolved board is equal to, we'll call this function forced move check. That's going to take in the unsolved board. Now after that function's run, this is where we check. So we say if original unsolved board is equal to our unsolved board, then we want to continue. So what we're going to do is we're going to say if it's not equal to it, so if it's changed, then we just want to repeat. So we want to repeat the basically the steps we've just taken. So I'm not certain this works, but I'm hoping it does. I'm hoping we can just call the same function again, passing in unsolved board. I guess we'll see when I get to it if that works or not. And then if it's equal to it, obviously there's been no change, so this is where I'm going to comment this out because this is like we're not going to have this function yet, we're not going to write this for a while, but basically run next function. So this will be like the next method of solving. Then at the end we're going to return unsolved board, which obviously now will be a solved board, or it will be as good as we're going to get. We could always do like at the end of our list, we could do some sort of check, so we could say if there's still a 0 element in the board, we know it's not solved. We could do like a series of checks to check has the board actually been solved, or are our algorithms just failing to find a solution. So now we need to write this function here, so force move check. Now this function is probably going to be the biggest function we've done so far. This is going to have to loop through. The way I've done this before was very messy, but basically it's going to loop through every cell in the array. I'm not sure, every element I guess you would call it. Every element in the array, and it's going to check for every element. So we say R here. Is the element to the right of it a 0? Is the element below it a 0? Is the element to the left of it a 0? And is the element above it a 0? So if I go back to this board so we can actually see the board, so we see red here. We know red doesn't have a force move because it can go right or down. I might actually pick a better board than this, one with like a force move in the corner. Come on, there should be one somewhere. There we go, so blue. Blue's now forced to go right, so if we run this, so we can see for blue we've only got 1 0 here, so that has to go there. Now what I'm thinking is for the ends, because it's important to identify what's an end and what isn't, because if you see me do this and then we run it, okay, so that one failed because it's not picking up the lines properly now. Is there another one I can do? It's only going to go down. Let's just say I do this, and then run. Nope. There we go. So you can see here we've got 3 greens in a row. They're all little g's, like lowercase g's. So I don't know, like the program would have no way of knowing, like, can we move from this end, or like can we move from the middle maybe, or can we move from the end? So we need some way of telling the program where its ends are, so like where it can move from, so obviously the ends. So my thinking is, what I did in my other one was, once we move, so we'd start out here, this would just be a lowercase g. Sorry, we'll start on blue because blue's forced, so this is a lowercase b. Now say we get a force move and we go to here. Now we've made a move, so what we'll do is the move we've just made will capitalise the previous square, so this would now be an uppercase B. And now we would know in our program, right, uppercase B's are not ends and they cannot move. So we're going to have to code some sort of way of checking that in, and then after the fact of moving uppercase, like the letter we've just moved from. It sounds quite complicated, but hopefully it'll make sense when I get around to it. And we also need a way of checking when we have ends together if they should join. So if we have like this here and we know these need to join, we need some way of joining these and then capitalising the whole line so that the line's then done. And the idea is that once we have a full board of capitalised letters, we know that we've filled the board and we have all ends joined. So we're probably going to want a for loop. So for I in, okay, so we're going to have to pass something new in. We're going to have to pass the size of the board. Maybe. Actually, no, we could get the size of the board from unsolved board, I guess. But it's probably easier to just pass it. Let's pass it in. So, size of board. Size of board. Size of board. And size of board. So for I in range, size of board, and for j in range, size of board. Now we want to check every square, so we want to do unsolved board I j, and we want to say for that square, are the squares around it available to move into? So if unsolved board, and we could say I minus 1, this would do the, if I remember rightly, numpy does like y's and then x's or something weird, but basically this is going to be either the square above it, the square above the blue, or the square at the left of the blue. I'm not sure which one. But if we say if this square is not equal, not equal to a 0, that's going to be a 0 like this, I think it'll pick it up like that, then we know it's empty. And then we're going to basically repeat this for the squares around it and see are 3 of them empty and is only 1 of them able to move into. If so, move into it. So what I'm going to do, I'm going to pause this video and come back once I've typed this up and worked out the logic, so you're not just sat here listening to me try and figure it out on the fly. So yeah, I'll be back soon. Okay, so I figured out that the way numpy handles column matrices, or arrays, sorry, is basically board with x. If say you've got a 5x5 board with x, we'll call this unsolved board, that's the one you've last seen. So unsolved board, and then 0 0. Now this is a 5x5 matrix. This is actually equal to unsolved board minus 5, which was going to cause problems for the way I was planning on doing it, because what I was planning on doing was using a minus 1 index to detect like over here, so you can see sorry, up here. So if we were going to be checking the minus 1 element, I was hoping this would return like a non-value or something that we could easily identify as not a 0, but it turns out it doesn't. It actually, when you got a minus 1, it returns something down from this bottom corner, so it was causing issues. So what I decided to do was create a new board, and that board is board with x. So you can see it here, I printed out. It's basically just the exact same board but encased in rows and columns of x's. So when I go now to the minus 1 element, it's going to have an x returned instead of whatever minus element it would have been on the opposite side. So to create this, I've just done board with x is numpy.zeros, size of board plus 2, size of board plus 2, and then data type string. So that creates a 0 array that's not twice, 2 columns and 2 rows bigger than the array that we want to end up with. So then what we do is we loop over that twice, and we replace on the first one everything we replace with an x, so then we get a board of x's, and on the second one we replace everything in like the center part, so from the R here to the 0, everything in that sort of rectangle around here, we replace all of that with this old matrix. Basically that's what this little loop here does, and then you can see we print that out, and when I run that, you can see we get the same array just encased in x's. So now I'm hoping we can go back to this style of solving it, and hopefully it's going to work this time. So yeah, that's where I'm at so far. Yeah, I'll pause it now, finish some more, and then explain what I've done. I should also mention we've changed the limit in the range function down here to be between 1 and the size of the board plus 1. So this is going to mean that we're not looping over the first row or column, because obviously that's got x's in, we don't care about testing that, and we're not looping over the last one, which would be size of board plus 2, because again that's got x's in, so we don't care about that. Okay, so what I've done now is if the board with x, basically if the -1j element, which is the element above the blue, so you can see here it's going to be like this element here, which obviously is going to be an x in our array. Now if that is not equal to 0, which obviously it won't be, it's equal to x, and the one to the left is not equal to 0, which it won't be, it'll be an x, and then the one below is not equal to 0, which it won't be, it'll be green in this case. And the one to the right is empty, so basically if only the one to the right is equal to 0 and all the rest aren't, then the one to the right is going to be equal to the current one, so they're both going to get changed to lowercase b's, and then the original position, so the position we're checking that's now being moved, is going to be capitalized to show that that's no longer an end and can no longer be moved. So hopefully what this is going to do, we might have to add some sort of logic to let it know that it can only move ends. I'm going to add that in a second, but basically if you see what this does, I can run this now and you'll be able to see. So it's going to loop through and check if there's any right moves available, which you can see here it's capitalized to B and it's capitalized to G, because both the blue and the green are forced moves. So yeah, we know that's working, but now obviously we've got a problem of if we run this twice, it's probably going to start moving the capital B's over when, yeah, we don't want that. So I've got to fix that next. Okay, so the next bit of logic is I've added in characters that are ends up here. This should be all the characters in lowercase that are available to be the end of a flow, so available to be moved. Now I've put this in the solve board bit because I would imagine we're going to need this again in other functions. So this is up here and then we just pass it into the unsolved board function over here, accept it over here, and then the little line of logic that uses it is I've just added an if statement here, so that if the board with xij is in there, then we actually check this condition down here. I didn't add it as an and on this because I'm not certain, but I would imagine it's quicker to just check this for all of them than it is to check all 5 conditions. I figured that might speed up the process a small amount. It's probably negligible, but it also makes it a little bit easier to read, I think, because this is sort of, even though it could be put in this line here with an and, it's sort of like a separate criteria you're checking, so I'd prefer to have it in a separate line to make it obvious that, like, why and whatnot, like why you're doing it. So what I'm going to do next is that's going to check for right moves. Now we need something to check for left moves and something to check for up and down. So basically I'm just going to copy the same code. So check if we are forced to move left. Now I'm just going to copy the exact same code and then just change the indices around, or the indexes. So basically all we'll have to change is the -1, the +1, like basically these 2 lines here. As long as we change these, then it should work. We actually won't even need to change these -1, +1. What we'll have to do is change this to a not equals, and then change, so we want to check if we're forced left, so we want the left cell to be available, or the left array to be available element. So this is the j-1 element, I think. So if we check that, then if it is, we want j-1 to be equal to this, and then that should be right. So if we find a board where a left move is forced, so right here this red's forced, so if we save this and then run, we should see that the red moves. So it does right here. We've also got greens being forced around over here. You can see like already just with right and left moves we've got quite a bit of progress. Got the orange being forced along. But yeah, these greens you can see are still lowercase, even though there's ends right next to each other that have to be joined, because this green is forced now to go up. It's not actually realising that, so we need some bit of logic that's going to check if two ends are next to each other and one of them is forced to go to the other end, then we need it to realise. So that's probably going to be what I'm going to do after I've copy and pasted all this over. So I'm going to do this off the recording for now. Come back once it's done. Okay, so I've copied those over. I'm going to run this, see what it comes out with. So you can see again we've got these false moves, and you can see it's made a mistake here. It's made the green go up, but this mistake only happened because this cell got filled by a green where it should have connected them. So we're probably going to need some sort of function that will check if there's two ends next to each other, check if one of them are forced, check if they need to match up. I'm not sure how we're going to do this, but I'll get back to this after this video, so probably be what we do in the next video. But you can see we've got different false moves going on in like different directions. We've got this orange is forced upwards, we know up's working. This blue's forced upwards. Let's see a down move anywhere, but see if we can find one in here. Okay, so here we've got red's going down, green's going down, so yeah, we see down's also working. So yeah, next video we're going to be looking at how to join ends and make sure it makes no mistakes like that. It's probably going to involve a little bit of messing with this code, I would imagine, to check that it's not equal to 0, or its own colour maybe, something like that. Yeah, that might be a good way to fix it actually. So yeah, we'll come to the next video. That's it for now. See you in the next one.